that's what converse and inverse and all that's all about. So now I've said that the contrapositive, in fact, is in fact equivalent to the original statement, and I got no pushback from that. Probably because you guys respect me, right? And it would probably be kind of a jerk move to immediately start to question it, right? But now it's time to question it. So let's think about why it's true. Why is contrapositive equivalent to original? That's the big question. And all of those letters are terrible, but I think the general shape of the word actually looks correct. This is like impressionist writing right here. You squint, you see it. The point is, why is contrapositive equivalent to the original? Well, think about this. Assume A equals, not equals. Assume A implies B is true. Then, if not B is true, let's think about this. So A implies B is true, meaning whenever A is true, B is going to follow. Whenever A is true, B is true. If not B is true, then firstly, B is false. Then B is false. Right? That's just simple. But now let's think about this. Consider if A were true. So let's consider for a second if A were true. If A were true, what do we know about B based on this?
B also, actually, I was gonna say, it also has to be true, but I don't know if that's true.
No, you're totally right. Because A implies B is true, because this is a true statement, then since A implies B is true, by the definition of the truth table, right? If the first thing, if A is true and the statement is true, Q must be, like the second thing must be true. I mean, what I'm saying is if A implies B is true and A is true, then B must follow. So since A by B is true and A is true, B must be true. So I'll put it this way. I'll say assume this is true and also assume not B is true, which implies B is false, which means B is false. So in this case, we're assuming A implies B is true and not B is true. If we consider A being true, that would mean that B must follow. B must also be true. But we assumed not B is true, meaning we assumed B is false. However, we assumed B was false. So A cannot be true. So the point is, if A were true, that would mean B is true based on this, but B is false. So we can't even have A be true. Like that just can't happen. It leads to a contradiction, right? B can't be true and false at the same time. Why can't B be true and false at the same time?
Then it wouldn't be a statement?
It wouldn't be a statement. Exactly. That's this day one coming back. Day one, we said a statement has to be true or false, or actually day two. Day two, we said a statement has to be true or false. It can't be both. We said that's the law of the excluded middle. And I kind of told you guys, like, hey, this is just what we're going to assume. Everything in this class we're dealing with statements. It doesn't necessarily mean it's true. It doesn't necessarily mean it's like true with the real world. That's just how we're going to work in math. And so this is true and so this is true if you assume the law of excluded middle. If you assume that things can't be both true and false at the same time, which isn't that bad of an assumption, then you know the contrapositive is the same thing as the original statement because of this right here. This makes sense? All I'm saying is that all I'm saying is that if A and B is true and you have not B, A can't be true because that would lead to B, which you know is false. Meaning, thus, not A must be true, because if A is not true, not A must be true. So, not B does lead to not A. It's kind of confusing, but I hope it makes sense. And think about it this way. Assume this is true and assume not B is true. You have two options for A. Either A is true or it's not true. If A were true, though, it would lead to this contradiction. If A were true, then because of this, you know B must follow, so B is true. But we specifically know that not B is true. We know that B is false. So since the only options for A are true and not true, A must be not true, and so then you have that this follows. Does that make sense? Well, anyway, let's not get too hung up on if that exact explanation makes sense, because we're not just going to leave it to that explanation. We're of course going to prove it with
Truth table.
Oh, truth table. Wow. Dutch angle for a second. Does someone type in truth table? There we go, with a TT. Thank you for that. Yes, with a truth table. So, real quick, let's have P. Let's have Q. Let's have not P. Let's have not Q. Let's have P implies Q. And there's a lot of space for that. And let's have not Q implies not P. All right. So you have this, and the case you have to consider again are true, 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 false, false, true, false, false. So the first three of these are easy. So if P is true, not P is false. In the case where Q is true, not Q is false. And then P implies Q. Remember, P is true and Q does follow. So this is true. And you can look at this truth table, the definition of if and to figure it out. Or maybe I'll put here, this is like if then, if you plug in true, true, which will come to true. Not Q implies not P. So here, this is a conditional statement where you're saying not Q implies not P. So this is like taking this if then operation and plugging in not Q and not P. And then that would be not Q we know is false. Not P we know is false. And so you plug false, false into an if then, oh, that's true. It's vacuously true. So we get true, true here, that's good. Any questions on that? Because if not, we can blow through the rest of this because the rest of it's just the same basically. Good. So then in the case where P is true and Q is false, not P is going to be false. Not Q is going to be the opposite of false, which is true. P implies Q is false. This is the one case it's false because P happened but Q didn't follow. And then here you can think about this as it's if then, not Q, not P, which is if then, not Q in this case is true, not P is false. So here we're going to get, the true false thing where you plug the T is the first one and that false the second one, and that's false. Only case where it's false. And then it keeps going like that. In the case where P is true and Q is not true, when P is false and Q is true, you get not P is true, not Q is false. Since P is false, P implies Q is vacuously true. And then here, this is like if then, not P, Q, not P, not Q, not P is false, not Q is true. When you plug a false true in, you get vacuously true again. And then finally, If you plug in the case where P is false, Q is false, not P is true, not Q is true. P implies Q is vacuously considered true. We're in the false part here. And then here we have if then, not Q, not P, not Q is true, not P is true. And so if you plug in true, true, and if then, you get true. So these two columns are the same, meaning I hope the explanation of why they're the same makes sense for their intuition, but if it doesn't make sense to you, just believe it here. The truth table is the same, so they are true. Any questions on that? Perfect. Cool. Any comments? I mean, this is kind of interesting. Like, I feel like when we do the truth tables, it just kind of feels like we're doing a bunch of computation. But really remember what this means. This means that P implies Q is the same thing as saying not P, or not Q implies not P. This is incredibly powerful because this is the first one we've really done that's not entirely obvious. Like, it's not entirely obvious that not P implies not Q is the same thing as P implies Q. And so here's where we can really, I told you before, like the reason you want to rewrite a statement, like using the equivalences, like we had our laws, you can rewrite them. The reason you can rewrite a statement, or like one reason you do it is because sometimes it's easier to prove the truth of one than the other. This is one where that can really be true. Sometimes it's a lot easier to prove this than it is to prove this. Even though they're equivalent, it might be a lot easier to see this solution and this solution. Which is interesting. Yeah, and you guys will see all that later. But we're going to call this the contrapositive law, by the way. This right here, the fact that the contrapositive is equivalent to the original, we're going to call this contrapositive law. So if you ever use this in like an argument, like one of those statement things, one of those statement proofs we went over, we had to do like by this and the equivalent by this and equivalent by this. You can say by contrapositive or by contrapositive law. Sound like it. That's fine. Yeah. So I'll say, is there a chat message? Yeah, look at that. Marcus has an excellent chat comment. I'm not going to say it out loud. You can read it. Actually, I'll say it out loud. I'll say it out loud for the people at home. Can we prove that inverse and converse are equivalent by just saying that the inverse is the contrapositive of the converse? I think that's a good idea. However, I'm not gonna tell you because it's gonna be one of your homework 2 questions. I'm gonna tell you the fact that not P implies not Q is equivalent to Q implies P. And we'll call this inverse converse law, but proof for homework. But it's not hard. All right. Anything else? And remember, none of these are the negation. So